All right. So, this is your office hours. Yes.
Gotcha. Can we do number 3 on homework 4?
Did you not see that I posted the solutions today?
Yeah, that's true.
Yes.
Could you give us, could you first let us know what test 2, like, what the topics are?
Stress considerations. These will include, so exam 2, I'm going to write exam 2 review. These will include topics of thermal, 3D stress strain, composites, because one of you emailed Professor Simon, I created a statically indeterminate problem. I'm joking, by the way. I just added one on there because I can. And stress transformations. All right. Now, if I am being completely honest, you will not get a full-fledged problem on this, on statically indeterminate. So I will not be giving you guys necessarily a full-fledged statically indeterminate problem, but it may arise in the true-false questions. All right? For example, I may give the equation for compatibility, or I may give you guys a little figure that tells you, okay, is the summation of these two systems equal to this system? In which case, then you guys would have to tell me yes or no. So it's more of a conceptual thing, but I'm not going to be having you guys do the math for it because I understand that solving one problem in itself takes about half an hour to do if you're not used to doing the problems. So really, I would say for the math portion of the exam, like doing the actual calculations themselves, I would say focus on items 1, 2, 3, and 5. All right. I'm going nice on you guys. Yes.
Will you have us using the circle method, or can we use the equations?
For stress transformations, you can use whatever method you want.
Okay.
Yes, I am not going to ever ask you guys to use any particular method. One of you, interestingly enough, on the previous homework, I do have it, but I don't have it graded. But I have uploaded all of the homework solutions, so hopefully everyone has access to those and can watch them. If you want to see what you got wrong on your previous homework 5, I do have them marked up. I just don't have grades or points assigned to any of them yet because I still have to look over like 1 or 2 other students. But yeah, I'm not going to force you guys to do any particular type of problem or method for solving it because one student actually, he solved it very weird, but he still got the same answer. He did it through a term called stiffness, which is interesting because stiffness is defined as EA over L. I did not cover this because it is far beyond what I want you guys to really understand, but he somehow managed to get that to work. All right, so I could do, yes?
Could we do the 3D stress strain?
3D stress strain? No. Sure thing. So, let's do an example for item 2. And for this, let's have a rectangular block. I'm going to draw it out real nice. Let's come up with some arbitrary dimensions. Let's say that this is, nope, 2 inches by 4 inches by, I don't know, we'll say that this is like 8 inches, 248. And it is subjected to forces of 3 kips and 10 kips. There's going to be an equivalent stress going through there, equivalent stress going through there. And then we'll say that this is 1 kip. And so what I want, well, let me first define a coordinate system. We'll say that this is X, Y, and Z. What I want is for you guys to find epsilon X, epsilon Y, and epsilon Z. I'll give you guys 10 minutes to do that. And that's what we're going to do. I'm just going to make you guys solve the problems. Then we'll go over it. Point. Yes, you're right. What material do you guys want to use? You want to use glass? Brass. All right. I was like, glass. That's not going to deform. That's going to shatter beforehand.
Yeah, can you do a material that does something like that or not?
I want to use wood. You can do brass, but I want to do wood. This is going to be Douglas fir. The man, the myth, the legend. No, I wish I could, but those don't give me a modulus of rigidity. And you need the modulus of rigidity to calculate a very particular thing.
What would happen if you tried to calculate a deformation of shadow?
Well, the thing is, with these equations, they assume linear elastic behavior. So because of that, the equations don't care if the material shatters or not. If it exceeds that linear elastic limit, like if you plotted like the stress strain curve, right, and you calculated a point that was like just off the curve at all, then the material doesn't work, right? This is where that classification comes into play, because then like it becomes a very complicated thing. And so with computers, it would have to be continually running iterations, and it could run like 100,000 just to try and get the correct answer. So it becomes a nightmare.
Sounds like a great time.
It's not a great time. I had to do it for my master's project with rock. It's awful. Mm-hmm. Yeah.
How long would that take?
An entire year. And my entire master's calculation package was like 500 something pages.
Throw into engineering, I say. That's all you.
what pisses me off is my friend, he managed to do his entire master's thesis in like 5 pages. I was like, what the heck?
What did he use?
I don't know. He didn't have to, he did his on an entirely different project. I got jealous. I was like, why?
Yeah, I wouldn't know what to. No, you know what happened was you were definitely committed to it. You're like, that's the one I want to do. It sounds cool. And then you got knees deep in it, and you're like, damn it.
It is cool though. I am glad that I did it because the project is actually gonna potentially get built.
Yeah, that's good.
Mm-hmm. Yeah. It's gonna house a giant gravity battery.
I don't know what it is.
They drop this several thousand ton weight into the ground and they use regenerative braking in order to produce electrical energy.
So we get it, but like,
What?
I'm trying to like think, like visualize how that would. Like, okay, regenerative, whatever, like, okay, you think about like a car, you know, like doing the braking like that, or like you mean in the ground.
Let me see. Yeah, this is the thing I designed. They have these gears. Basically, as the thing drops, the gears rotate. And so because of that, it produces electrical energy.
But how does it reset?
It doesn't. It has its own it uses its own electrical power to get back up. But because of how fast it's able to go, it's actually able to produce a lot more electrical energy than it is.
That's pretty cool.
Mhm.
That's cool.
Yeah. Just one drop from that thing, it's a mile deep shaft, is enough to power, I think, an entire city for about a month.
That's really cool.
Mm-hmm.
Yeah, we
The
should-
only issue is it's probably going to be a shit ton to build, which is why it's like, no. That's why the state is kind of like, pushing back on it right now.
I would build that, bro. If you
I hope
need
so.
energy, you need it in multiple ways. You can't
know.
just pick one. You can't.
Do we get epsilon x, epsilon y, and epsilon z? You did?
No, I don't have nothing. I don't have a calculator.
You don't? Oh.
I ain't got my
All right.
legs.
You get to use my calculator, but you have to.
Don't even waste. I don't have my notes, so I don't even know what I'm doing.
Okay. Sit with someone.
Sit with someone?
Sit with someone. Work with them.
Sweat. Makes sense.
Mm-hmm. On full 110% effort. Yes.
So, you would need these, right?
You would mean you, yes.
That's basically it.
This wasn't your birthday, so.
But,
E over 2g minus 1.
Okay, that makes sense, then yes, I got that.
We should do it.
Yeah, which is, it's a lot. That's if it's multi.
Question? Why do you sound depressed?
Because I'm really confused now.
Okay, there's no need to be depressed though.
Okay, this is a calculator though. See, I plugged in everything that we needed for this one.
Yes, I noticed the issue. But the reason being is this, here, the way you plug it in. Because what it's doing is it's taking this whole thing and then just multiplying it by this. So you're getting really high each time. What you need to do, and I recommend this, press alpha, y1,
I got 8.5.
and you get a fraction.
This one is so.
You have to press alpha,
What's it?
begin, and y.
Because I was like,
Then it pops up.
I kept checking it to see if
Press
it's.
enter and it
Yeah,
gives you
because
that.
it's like,
When I do that
Oh,
on my
yeah, it's for
Why?
X, Y, and Z, yeah.
like I can
Yeah,
have the function to the fraction, but then it gives me my answer in fraction, and I have no idea how to convert it into decimals.
It is annoying, some calculators, like my calculator does the same, or gives it to me in scientific, so it aggravates me. That's why my favorite calculator is always
oh,
Excel.
yeah, that's what
Because it's -1, and then it's 2 and everything.
Excel?
Oh, okay.
Yeah.
Yeah,
It's sad, I have to plus 2 plus 2 into Excel, just to make sure.
because it's supposed to be 1 divided by 6. Oh shit, you're right.
You got that for, which one?
Yeah, hold on.
I should get .07.
Yeah, that's,
Which
I'll
one
put
you
it
get
in.
that for?
Huh?
Which one you get that for?
Z.
Yeah, what was that ratio for,
Python's ratio, yeah.
yeah, so you take, you need the two elasticities of two different materials?
The modulus of elasticity and modulus of rigidity.
Okay, yeah, so it's the elasticity with the length on top over the rigidity?
I believe it's E over 2G minus 1. Right? Is that the equation? Where's my phone? You got it? Not yet? Alright.
Which one? No, I had it wrong. That's what I got with that.
Is it supposed to be unitless or is it?
Python's ratio is always unitless, yes. And Python's ratio is also never negative. So if you're getting a negative value for Python's ratio, it's wrong. I mean, it can be negative, but for this class, it will never be negative.
What was that other ratio we did when we took, this was with the composite materials, right?
The modular ratio.
Yeah.
It relates this elastic moduli of one material to another.
Yeah, so if I wanted to figure out.
Right, 'cause I just got these two
The larger.
The larger value usually goes on top, yes.
Yeah, okay. I just wanted to make sure.
Yeah, that's this dimension. You're doing this one here.
So it's in the
It's going that way.
We can cuddle though. What's wrong with me? You should never use something. No problem.
All right, all the solutions should be uploaded to Brightspace now. Yeah. Homework 4, 5, 6, and I also technically didn't upload homework 3 for some reason.
I saw you do 3 and 4 on the same
I did 3, 4, 5, and 6 today. All. Yes.
This one be
What? We take the entire cross-sectional area, so it would be 8 times 4. Then sigma y
Yeah.
would be 2 times 8. And then sigma z would be 4 times 2.
So you were right about that.
Okay.
Where did you go for that first one?
Well, sigma x here would be 4 times 8.
Sigma x or epsilon x?
Epsilon.
that's because of this.
That entire area. Yeah.
How did you do it?
So.
And then just
when I
keep in
did-
mind the direction of signs with respect to whether it's compressed or tension.
So then I divided it by- I didn't put it
That
in
will all
that
work
one
together.
because it's gonna be confusing.
Oh, good, you got this. I'm not even that one.
That is not.
Yeah, for x.
Yeah.
Okay, that's for x.
He just said her big cat
This is what,
Oh, wait, well, yours is in a different form.
yeah, mine is in the, because I didn't. This is.
You got that. What's your background?
Correct.
Yeah, for x. So you could just do all of them like that, right?
Yeah, I look like I know what to do like that.
But what was like that other, like really long one?
That's the one that I was trying to do, but I didn't get the same answer when I did.
Yeah, what's up?
Or I did, and it just doesn't look the same.
Yeah.
So can you just do stress over the modulus of elasticity for all of them to get the strain?
It's the same thing, but it must be.
No.
I think you plug in for.
The reason being is because the stress of each one is going to contribute to strains in all 3 directions.
Okay.
Right, so that's why we have the 3-dimensional strain equation. If you remember, is epsilon x is equal to 1 over e times sigma x minus nu sigma y minus nu sigma z. It's because sigma x and it's because sigma y is going to contribute to epsilon x, and sigma z is going to contribute to epsilon x, just through the lateral deformations.
So wait, when would you have to use the stress over the elasticity? Like when would it be appropriate? to-
Only for the normal strain. So if you wanted to find, for example, the strain due to axial loading only, it just happens that in these problems, I gotta find a way to explain it.
So very good. This is what I'm
in a case where you have a problem,
Or 4.4.
in a case where you have a problem that looks like this, right? There's going to be lateral strains also, but this would be like sigma z. So then sigma, if you wanted to find what the epsilon z would be, epsilon z would just be the same as epsilon, which that is just going to be sigma z over E, right? And then there's also going to be sigma x's and sigma y's, but if those aren't defined, assume that they're 0, in which case then, yeah. So what you're referring to is uniaxial loading, which doesn't apply to this problem because we have 3-dimensional loading. So all 3 stresses are going to contribute to strain. I'll give you guys another 5 minutes. You guys should have epsilon x, y, and z now.
Why is negative?
What?
Why?
All 3 values should be negative. They're all causing compression on the material. Emily, use the sheet that we made. Does have all the equations. Oh, you are? Oh, nice. Next week is the fun week. Beams.
It's not gonna be fun.
Beams are the most fun. I love beams.
Yeah. Should marry him.
Mm-hmm. My professor used to say, be the beam.
Like why?
I don't know.
So I know people just start randomly planking in the class.
I guess so.
That's fine. No, bonus points. See who can plank longer. Me or you. Just think about it.
I got a 8-minute plank by really early. So this was just happened. Yeah, it's actually, I got 0.005. Can we do a composites next?
Yeah, sure. All right, everyone should have calculated it by now.
I got the first one.
You got the first one? You should be able to calculate all 3 in like 5 minutes.
I don't know about adding 2 more questions. You might have to take 2 more questions off the test at this point.
All right, so let me ask you guys this. What did you need to do first? Find Poisson's ratio. What was that equal to? E over 2G minus 1. What was that equal to?
8.5.
What was it?
8.5.
E over 2G minus 1 is equal to...
It's gonna be anything.
Is it 8.5?
No, it doesn't mean
Yeah, it is.
Is it really?
You did it with me.
That is sus. I need a calculator. Give me a calculator. Nah.
Yeah, I'll trade for 2 bonus points.
I gotta see this. 8.5? Poisson's ratio should be nowhere near that big.
It's 1900 and then 2 times 100
Minus
minus
minus 1. 8.5.
Let me look back at the notes. Because that throws me off
That's what it says. E over 2G minus 1.
in the notes.
And I did it like 5 times.
No wonder why it took you guys so long. All right, we're not working with wood. All right.
Use the brash, but
We'll use brass then. We'll use brass and I'll work through it really quickly, just so that way there's reasonable numbers. That is interesting, but I guess.
Can we just use the wood?
What?
So many people have it done.
All right.
yeah.
For the values that I chose, okay. Well, I mean, I'm making these questions up on the spot. That's pretty difficult. Yeah, that's 8.5. That is really interesting. Because Poisson's ratio, it's probably because it's a very nonlinear material.
Wait, what about the material?
It's probably not, it's very nonlinear. So that's probably why.
What does that mean?
It's me talking to myself. That's what it means. Yeah, I hate these numbers. All right. Duly noted. Keep away from wood for these 3-dimensional problems. But as long as you did the procedure, so these numbers are clearly not going to make any sense. But if you follow the procedure, it'll be fine. All right. So epsilon x, you would just get 1 over 1.9 times 10 to the 3 times sigma x, which you need to calculate. That's going to be negative 10 divided by 2 times 4. Sigma y, I'll just write it out here just to make it clear. 2 times 4, which is 10 over 8, so negative 1.25. Sorry, not that one. I am losing my mind. Nicole was right. That's sigma z. So sigma x is going to be negative 3 divided by 4 times 8. Then negative 1 divided by 2 times 8. And then this is negative 0.06. Okay, I guess it's not too bad then. Okay. It's not going to be too bad because the lateral strains are actually really small. So epsilon x is going to equal negative 0.09375 minus 8.5 times epsilon y, negative 0.0625 minus 8.5 times negative 1.25, which will give you Does everyone get 0.0058?
Yeah.
Good. Do the same thing for epsilon y now. One over 1.9 times 10 to the 3 times. And this, everyone should have gotten 0.0060, give or take.
Yeah.
And then epsilon z, 1.9 times 10 to the 3 times negative 1.25 minus 8.5. Which this strain is going to be 0.00004. Is that what everyone else got? Okay. Those strains seem pretty reasonable then, given the weird moduli of elasticity. All right. Now, calculate delta V, the change in volume. That should be a quick, easy calculation. Were there any questions about the strain equations I used up there? Okay. First, I want to ask, what is everyone using to calculate the change in volume?
Isn't it like the initial times some of X? I mean,
Yeah.
the three string.
We didn't write that on the equation sheet. I would add that. What'd you get?
I don't know if they're right though, 'cause, like there's no initial, right?
There are units. There is. Yeah. What's the initial volume? Yeah.
Did you want the change or what it's at after
The change.
the change?
Yeah, because the final is just going to be whatever the initial is plus delta V. So 7.5 what?
7.5274 times 10 to the power.
Times 10 to the what?
Power of negative 4.
Yeah, but what are the units? Go to a contractor and tell them 7.5. You know what they'll do with those calculations? They'll look for the nearest garbage pail and throw it in there.
They don't even remember the test.
What?
They don't pay the test for the test.
No.
Are you being serious?
Wait, hold on, what? I just said no because. What was it you were asking?
Okay, let's say you're asking for this whole test. Is it okay to write that 7.52704 times 10 to the power of negative 4?
Yeah, you can write scientific units.
Okay.
All right, just be reasonable with the units. I don't want to see 7.508193772. Just 7.5 times 10 to the negative 4. That's good. What?
We want to be as accurate as possible.
I will throw your test in the garbage. Engineering is not about accuracy. It's about approximating to get things done. Mm-hmm.
That makes me uncomfortable.
Yeah. Just oversize a beam by a factor of 2, factor 3. There you go. What does accuracy need to do at that point? Nothing.
That's true.
Right? So V naught is just 8 times 4 times 2 times, you need the sum of this. This is going to be roughly 0.01184. Which, yeah. You get, what do you get? 7.5 times 10 to the negative 4? Is that what everyone else gets?
I got 0.75.
I got 0.76 cubic inches. What did you do? You just took your value and divided it by 1,000.
Well, I use the scientific version. That's what I have to do. It's really what.
Your exponents are like extremely large.
I got those exponents.
That's why it's ones are blocked. Well, what would you do without doing that?
You get partial. So what would I do? Right. This is where you're going wrong.
This body, part of those nine.
Where you went wrong, you're off by 1,000 because modulus elasticity, you did 1.9 times 10 to the 6. You put it in PSI, you left your stress in KS. Yes, you should have did 1.9 times 10 to the 3.
This makes sense to me.
Yeah.
This is like one thing I could say. The last one I got was
All right.
composite.
Now, everyone understand those equations, their applicability? The numbers seem a little wonky because I can't choose proper materials. So moving forward, I will choose linear elastic materials on the first page when I am making problems up. And I will do my due diligence if I choose second problems for the exam. But let us work on a second problem now. Example, and what Michael wanted to work on was item 3, composites. So, how many composites you guys want to work with?
Two.
At least two
Well,
or-
how many
I would say
use
two or
to-
three.
Well, you need at least 2 to make a composite.
Okay, so three or four.
I could give you guys 4 on the exam, 5 on the exam. I'm not going to, but I could.
You only use two, right?
What?
You only use two, right?
No comment.
For time's sake.
Doesn't take long. I could give you guys 4. It shouldn't take
Well, I
long.
mean, you can give two grade that equal the same, right?
If you guys know what you're doing, you should be okay. Okay.
That's the problem, we don't, so. Yeah, let's work with two, if you're good with that. Or we can do, no, three. Do three.
Just bear with me. I'm drawing 15 more of these.
You're good.
All right. All right. The bar is subjected to an axial force of, I don't know, 30 kips. So P is equal to 30 kips. Find the force in each material. And then you guys need dimensions, which I will draw out really quickly. So this is, I want to say 4 inches, 1 inch, 1 inch, and then 4 inches. There you go. I'll give you guys 5 minutes. 10 minutes, I'll be nice. It shouldn't matter in this case. If it was, I would specify if it was in compression or tension. But generally speaking, the only thing that's going to change is the sign of the force. So I'm really more so just looking at, can you guys properly assess the force in each member, whether it's in compression or tension?
That, is a tube or is it like a,
Nope. Solid. Solid stainless steel. It's a very thick piece of steel.
well, I'm saying is when figuring out the area, is it like, cause I'm picturing it like looking down in terms of not so much the section or,
Well, this is the cross section.
that's the cross section.
That's the cross section.
Oh, okay. I thought it was like a.
No, no, no.
Oh, okay.
That's the cross section. Yes. The steel. Okay.
Seal. I'm trying to make sure I'm not like messing it up, but then,
I wasn't scared.
like, I don't know.
You don't know if it's right?
Like it makes sense, but like there's so much.
Looks right. 28 times 6. Over. Well, the elastic modulus for brass is yellow brass is 15, yeah. Stainless steel is 28, 16, 8. So does that equal 3.73? Your entire procedure looks right.
Stainless steel is 28.
Times 16 divided by 15 times 8.
I think because of my calculator, I don't know if that's what I messed up on, or I don't know.
No. You are right.
I'm gonna try to keep doing
PB is right.
What did you say that calculator was?
It's a Casio FX115 ES. You can find them in stores for like $10. Some places are like pretty expensive with them, but you can find, if you look hard enough, you can find it for like $10.
Okay.
I think I paid like $20 in Target for mine, but which I am sad about because I then realized like 2 weeks later like they were cheaper.
What do you do? I have a question.
Yes.
Did you multiply the brasses by 2? So there's 2. And then this-
Depends how you're handling it. What is the area of brass you're considering?
1/4.
Okay.
So that's what I'm trying to figure out.
Um.
I think I just initially was.
But there's only 2 materials, right? Since there's
Yeah, there's 2 materials, but there's 2 brass elements
right.
there.
So like, if you were to put them together, would that be for the area then? Where you would do that?
It depends. So let's look at what you're doing.
I'm going based on.
It depends on how you're treating it, which is also going to affect your equilibrium equation. At the end, you should get the same answer, but
I'm confused. I'm missing something. I'm missing one piece of material.
materials are way wrong.
No, that's fine.
Where do you get 5,600?
Alright, so 15
Oh wait, I want to see this one.
this is what
Yeah.
we did.
But isn't just
Well, it's
29?
28.
Oh, it is 28.
Okay.
Okay.
28 for 15,000. Alright, so you're considering only one of these in the equilibrium equation, which means you would need to multiply your force by 2.
So then
Yeah,
this area.
yeah,
This
yeah,
is
yep,
16.
yep, yep, yep.
Is that what you mean?
No,
But
the
you're
area
missing
would be
this.
8.
Oh, yeah.
Oh,
Yeah. Otherwise, you could just relate the one walk to the other, right? But then your equilibrium equation is just gonna be 2 times the force in the brass plus the force in the steel. Otherwise, if you treated this as 8, then it would just be force in brass plus force in steel. So you can do it either or, it'll work.
Because I understand this way, the way we like do it. This is the one, but
Yeah, my recommendation is just sum up everything as one material as you can. Yes.
So, those lanes, that just be,
This is the entire cross section. Remember when I said that if you guys were just given cross section and length, just cancel out.
okay,
They're not.
So I
So
just
assume that the
assume-
length is constant. Figure it out. Good. Nice. All right. Think it's time to go over it, but I guess I'll do one more round. Each group gets one assessment. Write it out in your delta equation. So instead of just jumping straight over to that, just say that deformation in the steel has to equal deformation in the brass, which then is just PL over EA for the steel is equal to PL over EA for the brass. And then from there, you can just work out the algebra however you want. Right, so then this would just be PS is equal to P brass times ES,
You gotta lose your
AS, length of brass, divided by E brass, E brass for length of steel. I think it's something like that. I'm kind of like rushing through it. I believe it's this, but you can kind of see how I got from this point to this point, right? Always just start off with the most basic equation and just work your way through the Alright.
Which is not bad.
Otherwise, you'd have a million different equations written on your card.
Like you said, it's guesstimation, you just multiply it by this, and that factor times. No.
It's gonna be the vertical length because it's the length of the column, right? So you're assuming that this is a column, but, I mean, the column is a uniform cross-section, so because of that, you can just say that the lengths cancel. Make sense? Questions over here?
Oh, yeah.
Not yet?
Oh, yes. Oh, yeah. Oh, yeah. So I'm moving to compatibility.
Yeah.
But then how do the legs cancel? Why do the legs cancel? Just see here.
When you have a vertical column, the entire cross-section is affected. So unless I give you guys an actual column length with like different material properties. Yeah, in which case this, you have different lengths. But if you have just an entire cross-section, the length of all the materials is the same. So the lengths in the, well, I had it up right up there. When you set the deformations equal to each other, the lengths will always just cancel
These
out.
just cancel. Right?
Exactly.
And then PV, PS equals PV, and then E.
Yeah, exactly. Then it's just working out.
So just put
I gotta work through it.
Alright, so like,
But let's do it so that way you guys can take your break.
There you go.
Because I noticed a few students actually did it, so that's good. All right, so first step, we want to understand how the materials relate to each other. What is this process called? Compatibility. And what does compatibility tell us? Exactly. Deformation of the brass in this case is going to equal the deformation of the steel. We expand this to be the force in the brass times the length of the brass divided by the elastic modulus of the brass times the area of the brass is equal to same thing but for all of the steel. The lengths of the brass and the steel, because they are unspecified in this problem, will cancel because it is assumed that throughout the entire height of the column, the lengths of each material is constant. From here, we get that the force in the brass is equal to the force in the steel times EBR, ABR over ES, AS. You guys might have done it a little differently. That is perfectly fine. You could have related PS to PBR or however you wanted it to. All right. From this, you plug it in. So you got 15 times 10 to the 3, but that's going to cancel. The area of the brass is going to be 4 times 1. So it's 4 inches by 1 inch. And then I'm going to treat it with 2 materials. So it's 8 inches total. 8 inches squared total. And then the elastic modulus of the stainless steel is 28 KSI times AS, which was 16 inches squared. And what this should give you... What?
Wouldn't it just be 1.5 then, if you're doing it like that? Because it's 1,500 versus 28,000.
15,000 over 28,000.
Oh, okay. Maybe I'm just not bad. I'm just slow.
And this gives you 0.268 PS. From here, you plug this into equilibrium. Which will tell us that the 30 kips has to equal the force in the steel plus the force in the brass. So 30K is equal to PS plus 0.268 PS. 30 kips is equal to 1.268 PS. And so the force in the steel is just 23.7 kips. Who here got that? All right. Now there are two ways to be able to solve for PB, P brass. You can either use the equilibrium equation, where the P brass is just going to equal 30 minus 23.7, which you should get 6.34 kips. Or if you use this, you will get that 0.268 times 23.7 is equal to 6.34 kips. So either way, the answer should be the same. Any questions about this? No? All right, we're a little bit past our break time, so let's give it about let's give it about 5-10 minutes, and then let's reconvene no later than 7:30, so we could do like another problem or two. What?
How many more problems do you think we're gonna be able to do?
Probably 2. That's my goal.
Can we do a static in your tournament up
If you want to, I just said I wasn't going to put a long one on the
there?
exam.
You're not gonna put it on there.
Mm-hmm.
I forgot, I had like a little list written on my phone, just kept knocking down on my mind. Do that.
me check these numbers actually before I even. You guys, this just to do. Gonna change that number to 7-inch ink. There we go. It's fine. All right. This problem, this is a race kind of problem. Temperature is just continually increasing. I just want you guys to tell me what material is going to hit the table first, then second, then third. Yeah, it's a race.
Spice it up.
Yeah, it's a race problem. Determine the ranking order when you have an increasing temperature from 0 degrees as it's going up, what the order would be that the materials hit the table. Once you figure out that order, let me know. And I will add the second part of the problem. Yeah.
Is this like part of stress considerations?
Yes, it is. This is thermal.
Yeah.
Yep. Everyone got it? Figure out the ranking in which, who's the winner? Did anyone get that yet?
I got cast iron.
You got the cast iron as the winner?
Yeah.
How do you determine that? What'd you do?
So I did 1/8, that being how much it's supposed to form,
Mm-hmm.
equal to the coefficient times I don't have the change in temperature, but times the length, and then I just found the change in temperature from that.
And was for the cast iron the temperature the highest or the lowest?
It was the lowest.
Which would mean that it would make it first.
Okay, I didn't know. Oh,
Yeah, so you're right. Everyone understand what Edgar just did?
I understand, but like, yo, if like we were gonna put that doing the math, I would've thought the copper, because it's smaller, if it warms up quicker, you think it would expand more.
Well, that's why you got to do the math.
That's what I'm saying, that's pretty crazy.
So we can work it out real quick. So what we are going to have is our three equations, which is really just one equation, just repeated for each material. Alpha L, delta T. In this case, we basically want to find delta T. And what you should get is an equation that looks like that, which is just going to be 1/8 inches divided by alpha times L for each material. Now, alpha for the A36 steel is 6.5 times 10 to the -6, 1/degrees Fahrenheit. Alpha for the copper is 9.4 times 10 to the -6. And then alpha for the cast iron is 6.7, 1/degrees Fahrenheit. So once you plug those in, this is going to be for the steel. We'll get 1/8 divided by 6.5 times 10 to the -6, 1/degrees Fahrenheit, times the length of the steel, which is 300. And what did you get for the first one? Everyone see where I got that? Everyone should have gotten 64.1 degrees Fahrenheit. Is that what everyone got? For the change in temperature of the copper, it's the same thing, just using the copper as the material now. 9.4 times 10 to the -6, 1/degrees Fahrenheit, times the length of the copper, which is 200 inches. And you should have gotten 66.5 degrees Fahrenheit. And then delta T for the cast iron is you just repeat the calc one last time. And you get 46.6 degrees Fahrenheit, which means that the ranking goes 1, 2, 3. Make sense to everyone? Any questions about that? All right. So, part B now. Determine the stress in the cast iron once delta T is 1/8 of an inch for the copper. In other words, once the copper closes, that technically means that all of the systems are closed, right? So, I want you to determine what the stress in the cast iron would be. I'll give you guys 10 minutes to do that. Yeah.
What's the diameter of, or, I don't know,
You shouldn't need any geometry whatsoever to be able to find the stress. All you need to do is use the relationship between strain and the elastic modulus, and you can find the stress. My question is this: what would delta T be that you would use? Is it that?
Wouldn't it be the 66?
Or is it the difference?
It's the difference between 66.5 and the 46.6, right? Because then you're treating 46.6 as the initial condition, and then anything developed further than that is going to contribute to stress. Does that make sense?
Yeah.
I'll write that. Got it figured out? No. back at the equations that we worked on. That'll help a lot. Hmm? Old ones? Alright.
So, I'm getting this, I'm trying to, so, these 46.
The 46.6 is what is needed to close the cast iron, is to close that gap, right? And that's from 0 degrees. So, if you were to increase anything above that 46.6 degrees, then it would be stress developing because it can't deform anymore. So because of that, once the copper closes the 1/8 inch gap, the copper has to increase to 66.5 degrees, which means that stress is going to develop while the gap is still closing for the copper. So once the copper fully closes the gap, we already know the two temperatures, so just take the difference. Does that make sense?
I'm trying to make faces, because
Well, let me ask this, is the cast iron going to continue to grow in length as the copper is closing the gap? No. So, once the copper closes the gap,
oh, okay, no, I think it was I wasn't thinking about, since it's still increasing in temperature because of the next one, it's still putting
Yeah.
force, okay.
so now the real trick with this is figuring out what to use to figure out the stress, right? Which, the trick with that is look at your strain equations. Recall what strain is equal to. Yes.
So is that how you would do that?
What did you
So I gave you the displacement, and I did alter the length to get the strain, and then modulus of elasticity, which is stress.
over strain? And so that's the stress in PSI?
Yeah, in PSI.
That makes sense. Yeah, I think that makes sense.
Okay.
Cool. One person's got it, I think. I'm also like winging half of these problems, so I don't even know if that's the correct answer.
Okay.
It looks right. Let me ask this, how comfortable is everyone with Moore's circle?
Yeah, I think it was cool, right, figuring it out. So it would've been cool if you presented that first, because it helps with understanding, but I think I prefer the other way.
It's traditionally taught with the equations first more than anything else.
I definitely prefer the equation more than I prefer the circle.
Really?
So sometimes I just make it harder on myself, I don't know.
The last 2 semesters, the students love the circles more.
It's cool, it's a great visual, and it helped me understand a little bit more, but I don't, after like visually understanding what I'm doing, like then it makes sense to why I put things in the way they are.
Okay.
That should be like,
No worries. I'll give you guys another minute. Michael, you figure it out? John's the only one that's cleared it. No? What?
How come you doing different?
I don't know, I'm just confused myself,
Okay.
I'm ill prepared, so.
All right. Well, it's actually not too bad. Don't worry. All right. So, what we first need to do is we know what the temperature is that's increasing up until this gap closes. So, once that gap closes, we know that the stress develops for 19.9 degrees Fahrenheit increase from the copper. Does that make sense? Why we're using 19.9 degrees Fahrenheit? So, from here, you would calculate the change in temperature or the change in length of what the cast iron would be for that temperature increase, which would just be that 6.7 times 10 to the negative 6, 1 over degrees Fahrenheit, times the 400 inches, times the 19.9 degrees Fahrenheit. And John, what did you say you got for this?
0.053332.
Just like that? All right. So that's how much the cast iron wants to deform. Is it going to deform that much? No, it's already closed off. So stress develops. So one of the things that we need, because I don't give you guys an area, you could just calculate it as a force per unit area using the strain. The temperature strain is just going to equal delta T divided by the length, which is just 0.053332 inches divided by 400 inches. And what did that give you, John?
1.33 times 10 to the negative fourth.
It's a very small number, but it's expected for strain. From here, we know that stress is equal to the we know that the elastic modulus is equal to stress over strain, and we can rewrite this to say that the stress is equal to the elastic modulus times strain, which for the elastic modulus of the cast iron, I don't give you a particular cast iron, but which one did you use?
I used 10.
You used the 10 KSI, so we'll say that this is actually gray cast iron. So 10,000 KSI times 1.33 times 10 to the negative 4. And what did you get?
Well, I did a PSI.
Okay. What did you still get?
I got 1,333.3.
Yeah, so 1.33 KSI. Does everyone follow with that? The way you have to visualize it is this. All right, the gray cast iron is going to close off first. And then once the copper closes off, secondly, then this gray cast iron is still going to want to deform here, but obviously the table is restraining it. So because of that, there's a reaction force from the table that's pushing it back. Does that make sense? That's really kind of what the problem is asking. It's a little bit of a tricky word question problem. All right, I'm going to give you guys one more problem. It is going to be quick, hopefully. And this one is going to pertain to Mohr circle. Oops. all I want you guys to do is determine sigma 1, sigma 3, tau max, and theta p. You guys should get this done in 15 minutes. This is actually a pretty straightforward problem, this one. And this is the type of Moore circle problem you would probably see on the exam. You can use the stress transformation equations. You can use the Moore circle equations if you want to. It's fine. Actually, I'm going to change it. I don't want you to find theta p. Degrees. There you go. Now it forces you to kind of do both. And you can use whatever method you want. Has anybody gotten to the transform stresses yet? Sigma xt, tau xyt yet? Yeah, okay. Good. Keep getting thrown off. I keep thinking it's like a jar of honey. I'm losing my mind.
It's just peach tea. Maybe pretty cool.
Keep your head.
This part, yes.
You guys ready to go over it? Yeah? All right. Let's go over it real quick. All right. What did you guys get for sigma 1 and sigma 3? What did you get?
-3 and -5.
Wrong. Yeah,
5 and -3.
5 and -3. Look familiar? What does that mean about this stress state? the principal stress state. What do you think that would mean about theta P? How much would you need to rotate this block to get to the principal stress state?
20 degrees.
Nope. I'm just asking you for the transform stresses by rotating at 20 degrees. But how much would you need to rotate that block itself to get to the principal stress state from where it is now?
Plus or minus 45.
No, that would be for the maximum shear stress. Anyone? He said plus or minus 45, which is wrong. Well, the answer is 0. You don't need to rotate the block at all. It's in the principal stress state. Right? Sigma x is equal to sigma 1, which is just going to equal 5 KSI. And sigma 3 is equal to sigma y, which is equal to negative 3 KSI. The reason why we're able to make that assumption, make that guess really quickly, is because of the fact that there's no applied shear stress whatsoever. In every other case scenario, there will always be a shear stress, except in the state where there's a principal stress. If you are dealing with principal stresses, there's never a shear stress. So because of that, this is the principal stress. So that's sigma 1 and sigma 3 added away. If you guys did the calculations, you just wasted about 5 minutes. What about tau max, though?
4 KSI.
You got 4 KSI for it? Makes sense. You could have done that through sigma average, which you would have gotten 5 plus negative 3 divided by 2 is just, what is that, 1? Yeah, 1 KSI. And then you could have just done 5 minus 1 equals 4, or 1 minus negative 3 equals 4. Or the other way you would have done it is lambda is equal to 5 minus negative 3 divided by 2, which is 4 KSI. And then once you did 4 squared plus 0 squared, you would notice, okay, well, the squares cancel out, so it's just 4. So the real trick with this one was just recognizing that those were the principal stresses. All right, now for sigma xt and tau xyt, what did you guys get? Did you guys figure that out?
For sigma xt, I got 4.1.
Sigma xt, you got 4.1 KSI.
And then for txyt, I got negative 2.57.
Is that what everyone else got? Who here got something else or didn't get up to it? Don't worry if you didn't. All right. Well, yep, that would be the Mohr circle and the plane of rotation. So that would be rotated 20 degrees or 40 degrees on the Mohr circle, which would have given you the 4.06 and the negative 2.57. And then this is what that stress block would have looked like if you rotated it 20 degrees. Make sense to everyone? The way that you get that is just by using those really long equations. So sigma xt is just equal to sigma average minus plus lambda cosine of 2 times 20 degrees plus tau xy sine of 2 times 20 degrees, but tau xy is 0. So you would have gotten 4.1. And then for tau xyt, it's just negative lambda sine of 2 times 20 degrees plus tau xy cosine of 2 times 20 degrees, but that's equal to 0. All right, time for your get out of jails. I'm kidding. I'm not that mean. Just wait until 8:15. All right. Feel free to message me within the next 2 days if you have questions leading up to the exam. I do have office hours right before class time, so just let me know if you want to have office hours, do additional problems, or have any other questions. All right?